Okay, get some B-roll. Beautiful. All right, so we are here with Brian Beckman. Who
Yes.
are you? What do you do? What's going on?
Well, good grief. It's probably easier to describe what I don't do than it is what I do. I've done just about everything at this company.
Really?
I'm one of the latecomers of the original physics mafia that came with Nathan Myhrvold. That physics mafia included people like David Wise, who was the father of Windows.
Okay.
And basically, Nathan started a little company called Dynamical Systems. And the chief product of that company was a predecessor of Windows called Mondrian. Now, there have been more than one product called Mondrian, but I'm talking about the early 80s.
Okay.
It was a tiling Windows type of program. Instead of overlapping windows, you just tile the screen with Windows. At the time, IBM was doing something called Top View, I believe was the name of it, and so Windows were in the air. And of course, the Macintosh, the Lisa came out in the early 80s.
Mm-hmm.
It was extremely expensive, out of reach for most people. And even before that were the Xerox PARC workstations, the Dorado, the Dolphin. These were Lisp workstations with overlapping windows and bitmap displays. So GUIs were in the air, but not really for IBM PCs. People were still doing CUA, the character-oriented, 24 by 80 or whatever it was, 40 by 80 screens, VT100 kind of stuff. But Bill Gates desperately wanted some sort of GUI answer for PCs, so he bought Dynamical Systems from Nathan and their investors. Now, I didn't come with that original purchase of Dynamical Systems because I had a perfectly good academic career. I wasn't at all interested in writing mouse drivers for IBM PCs. Right?
Interesting. Then that's going to bring up the next question, but I'll let you continue.
Well, this is very ancient history, but it's still maybe some things of interest. But there were a bunch of physicists in the early times. Computer science was still kind of a curiosity as an academic discipline. Even as late as the early 80s, some of the first computer science departments were founded in the 70s. So most people who were in the computing business came from other disciplines. I was at Jet Propulsion Lab, which is part of Caltech, for almost 10 years before I came to Microsoft. I was doing software there, and it took me a long time to realize that I ought to be doing software at a software company than at a spaceflight company.
Understood. But you're solving a different problem here.
Exactly. Well, the kind of stuff that I did at Jet Propulsion Lab was research operating systems, to distributed concurrent operating systems.
Okay.
I'm probably best known as the implementer of the first version of the time warp operating system. I partnered with David Jefferson, who's the inventor of that, and Peter Ryer, who I think is still at UCLA. So that's a really crazy, wild idea in which you'll appreciate how a physicist could fall for something like this.
Sure.
This is an operating system in which processes can go forward and backwards in time. And a process going backward in time is like an anti-process going forward in time. If you're familiar at all with quantum electrodynamics, it sounds an awful lot like a positron is an electron going backwards in time.
Interesting.
Another thing we do in time warp is messages are always created in positive-negative pairs. So you create messages and anti-messages. And to cancel an incorrect computation, you send an anti-message chasing after a message. They annihilate in the input queue of the receiving process and cause rollback, cause anything to go backwards in time that needs to.
So is this a microkernel-based system or what?
Well, we wrote our own. We wrote absolutely everything from the silicon up. And it was designed, the specific goal was to demonstrate speed up for discrete event simulations, which is a particular kind of simulation. It's a little bit different from time step simulation that most people are familiar with. Game programmers, for example, almost always do time step simulation where the clock ticks and you track real time as well as you can, and if you can't, you slow down the frame rate and let the computer catch up. That's called time step simulation. Discrete event simulation is a little bit different. That's where you run the simulation as fast as you can with no link to real time. It could be much slower than real time. It could be much faster than real time. It's especially good for operations research, logistics, war games, that kind of thing, where you have multiple timescales all at once. Imagine a war game where you have soldiers marching at 4 miles an hour and airplanes going at 400 miles an hour and missiles going at 4,000 miles an hour. It's pretty dumb to time step the soldiers at the same rate that you're time stepping the missiles.
Sure.
So for simulations like that, applications like that, discrete event simulation is the preferred method. There's a bit more history here.
Mm-hmm.
You get me talking about this stuff, I'll talk all day. We'll
Go
never
for
get
it.
to current events, but the predecessor or the inspiration of C++ and of object-oriented programming in general was a programming language called Simula 67, and that was specifically targeted for discrete event simulation. So object-oriented programming, in a sense, is the grandfather of object-oriented programming is discrete event simulation.
Interesting.
Now, David Jefferson realized, along with some others, there was at the time a pretty vibrant research in discrete event simulation, that you could speed it up if you could run one simulation application on multiple machines. Today, I guess they call this mesh processing. This was over 20 years ago, though, so we didn't call it anything except multi-processing. Nowadays, there's multi-core,
Yeah.
which is tightly coupled, multiple heads on a single chip.
Mm-hmm.
And then there's distributed processing, which is multiple machines. So, for example, everybody knows Google, they've got 100,000 machines. Well, so does MSN. They got
Have some number.
on the order of many, many thousands of machines processing single applications.
Uh-huh.
So that's the kind of thing we were doing with discrete event simulation. And we wrote a whole operating system from the silicon up to do this. We wrote our own kernel. We wrote our own executive. Now, in those days, these days it sounds like, oh my goodness, did you do something of the scale of Windows NT with 450 million lines of code, or however much there is in it nowadays?
Mm-hmm.
No. The operating systems back then meant like DOS, which
Sure.
was something that you could write in 6 weeks and implement, get it running and debugged in a year. And it took us 3 years because
But I mean,
we had
that's a good
quite a lot
point.
going on. But
Yes,
yes,
you wrote a Windows is a general purpose operating system that's designed to be used in any number of ways, whereas you wrote an operating system to solve a specific subset of physics problems.
well,
Sounds like.
yes, that's true, but our programming model was completely general.
Okay.
We had a number of fun applications or debugging and test cases. One of them was the game of life, which I'm sure you've seen with the little creatures that, little blinking lights that run around the screens and so on. And we could run this in parallel. Another one, which was very interesting, was distributed air hockey, or pool balls, if you like. The challenge with problems like this is they're not inherently, they're not obviously parallelizable, because a pool ball scudding across a pool table could hit any other pool ball. So how do you deal with the fact that some of the pool balls might be on one processor and other of the pool balls might be on other processors? So there were a lot of fun research problems. But our real application was war games. We were funded by the Army, and just to share an interesting story from that time. Being on the academic side of it, our group was strictly non-classified. So the way those kind of things, the way those kind of defense-funded research programs work, is there's a veil, and the classified people are on one side of the veil, and the unclassified people are on the other side of the veil, and the communication is strictly controlled between them. The only difference, though, is that the classified people work with real data. They actually know where the actual missiles are in Kazakhstan, for example. On the unclassified side, we make up our own data. Well, there's Kazakhstan. There's a place. Well, let's put a few missiles there. So we just cook up our own data. But we work with exactly the same programs.
Okay.
And but I remember one day, I knew what the classified guys were working on. They were working on North Korea and the Fulda Gap, which is which was the way that Soviets were supposed that they would invade Europe, is through the Fulda Gap. And I can't remember exactly where that is. I think it's in Poland or East Germany, but it's 50,000 tanks driving through the Fulda Gap was the war scenario of the time.
Okay.
In 1989, the red phone rang over there on the classified side. 89, okay, 1989, and what came out the other end of it was drop everything, go to Kuwait. Now, nobody ever heard of Kuwait, right?
Yeah.
We're worried about North Korea and the Fulda Gap, which everybody knows has been problems since the 30s, right? The
Sure.
40s. So all of this Middle Eastern stuff was there. There were people thinking about this a long time ago. That's all I'm trying to say. Anyway, we had big war game simulations going on, and they desperately needed speed up because the way these guys worked were the generals would be in congressional committee meetings, and they would need answers right away. They would need to know what would happen if they closed bases in Germany, or if they had to move from Japan to Guam.
Mm-hmm.
How would this affect our war readiness? Well, these guys don't know. They have to run gigantic simulations to find this out. And when I say simulations, it's all logistics. It's about getting stuff from here to there. How long does it take? How many people do you need? How much does it cost? Military Airlift Command is the biggest Air Force, biggest package delivery system in the world. It's like UPS times 10. So they would get on the phone back to their headquarters and say, "Oh, what happens if from right in the middle of a congressional committee meeting?" And the guys would say, "Well, we can run the simulation. It takes about 2 weeks to give you an answer." Well, they didn't have 2 weeks. They had an hour.
Sure.
So they were desperately trying to speed up these simulations, and we sped them up by a factor of 80.
Wow.
Very big deal.
By being parallelized.
By running them on 128 processors.
Nice.
It was a very big success. And Gates heard about it. It was well known in the operating systems research business, and so after that success, I thought it would be a good time for me to reconnect with my old physics buddies like Myhrvold and David Wise, and see what was cooking at Microsoft. So I came in '92,
Wow.
right around the time that Microsoft Research was being formed. I was probably number 6 or 7 man in that organization.
So you were in the MSR.
Before it was called MSR, it was called ABDB, something or other in business development, advanced business development, something or other. I don't remember the exact name of it. But there were just a few of us. There was Rick Rashid, had just been hired, Nathan Myhrvold, Edward Jung. Peter Newport was one of the early guys there, who's now back at the company after having left and founded drugstore.com.
Wow.
Some of the other interesting guys, Gideon Yuval, very interesting guy who recently retired from Microsoft. He was there. So the first project we did was, I actually don't know if this is still classified at Microsoft, probably not, but it's now called BBT, was in those days called Lego. It was post-compilation optimization of a program. So the idea was that when you compile and link your software, there's live code and dead code mixed in. Now, compilers are smart enough to identify statically dead code. If there's some logical condition that can be calculated statically in the compiler and it can prove that this code will never be executed, it'll just throw it away. But the compiler can't detect dynamically dead code. And dynamically dead code is code that's never executed in normal scenario runs of a program. So, for example, think of Microsoft Word. There will be error handling code in there that's never executed as long as Word is operating normally. It's only executed under extraordinary circumstances. That's dynamically dead code. But the way programmers write code is they say, if error, do something extraordinary. If error, do something extraordinary. If their code just looks like that. As long as everything's fine, you skip over all of these do something extraordinary blocks. Well, that's dynamically dead code interleaved with your dynamically live code. It puffs up your address space.
Okay.
Virtual memory operating systems don't like that. They like it if your code is nice and squeezed together. So what you really want to do is take all this dynamically dead code and move it to some remote region of address space where it's never paged in by the virtual memory paging mechanism. You want your dynamically live code all nice and compact so that the the processor runs through that code in sequential order, roughly speaking.
Okay.
That's when the processors work best, if everything just goes in a sequence. It's called locality. So the trick is, how do you identify this dynamically dead code and get rid of it? And that's what we call post-compilation optimization. You instrument the program, run it through normal scenarios, it finds the dynamically dead code, it labels it, you unlink the software, squeeze it, and then relink it, and send this stuff off to Kazakhstan.
Okay, but so that begs the question then, since an exception is an extraordinary event,
Yes.
you have no idea when it's going to happen.
But you don't care.
But let's say exception A happens, and that code's been moved out over to Kazakhstan.
Yeah.
But I need to now run that code.
Yeah.
So how are you linking that?
Well, we reverse the branches.
Okay.
So imagine if you were, as a programmer, said, if everything's okay, do this. If everything's okay, do this. If everything's okay, do that. If everything, and then you got else. Nobody writes code like that because your ifs would be indented,
It would be insane.
off the page, right? But we turn the code into that. So by reversing the branches. That's the main technique. So you write code that says, if error, do something extraordinary. If error, do something. We turn that into if everything's okay, and then all the else's are way down at the bottom of your code.
Okay.
So it's as if you wrote the code that way. We reorganize. The compiler's smart enough, given these dynamic hints, and it's not actually the compiler. We do it at the LINQ level. It's called BBT, Basic Block Tuner. It's over there in Amitabh's organization now, and was a predecessor of Phoenix. The C++ backend doodad, and
pretty interesting.
and
it's a framework.
It's a whole framework, yeah. Because we wrote stuff that was just sort of hardcore, straight up, just get the job done, and then later on it was componentized and turned into a framework. So it's been in the works for almost 15 years now. So.
Outstanding.
Yeah, that was another big success. Once we did the first, that project, I think it was called Lego at the time. I know it was called Lego at the time. I don't know whether its name got changed to BBT while I was still working on it. In '94, I went off to work on public key security, which was the new hot thing. And after that, I went to Viper and did security. The thing about security is, if you ever do it, you get typecasted. It's a little bit like playing a villain in a cowboy movie. If you ever play the villain, you can never play the good guy again. Right?
True, fair enough. Depending on how good of an actor you are.
And it all depends. But once your face gets recognized, is Tommy Lee Jones ever going to be a good guy? Is Clint Eastwood ever going to be anything other than Clint Eastwood?
True.
It's typecasting.
Got you. So you got typecasted as
I got typecasted as a security guy, so I was in demand for a long time. I did some security architecture for Viper, which was MTS. But I started to work on freeing myself from security jail then. The main thing I did for Viper, well, let me go back to public key security for a second and tell you what I did there. The main thing I contributed there was a protocol called SET, Secure Electronic Transactions. It was an extraordinarily good idea, but it didn't quite make it in the marketplace, because what the marketplace wanted was SSL, the secure link.
Sockets layer.
Yeah, secure sockets layer, which is channel security. And what we were pushing with Visa and MasterCard was message security. And here was the fundamental motivation. Do you know where the majority of credit card fraud originates? It's a surprising answer.
I would guess post boxes.
It's crooked merchants.
Oh.
You give your credit card to the merchant and he sells it out the back door to the crack dealers. Yep, that's the majority of it. So what we wanted to do was make your credit card, your client user credit card numbers, secure against a crooked merchant.
Okay.
Merchants already get something from Visa. You know, when you run your Visa card or MasterCard through a Verifone or the little sliding scanner, what the merchant gets back is an authorization code. That's a guarantee of payment. In principle, he doesn't care about your credit card number. He wants that authorization code, because then he feeds that to the clearinghouse at night and gets his money.
Mm.
There's also a merchant bank involved. So actually 5 players involved. The user, the user's bank, a clearinghouse, a merchant bank, and the merchant. So it's kind of like a little pentagon of... And these guys are all exchanging messages all the time, and we cooked up a system for securing those messages individually and preventing the merchant, encrypting your credit card number against the merchant. So the merchant would get a cookie, a secure cookie from Visa that says, yes, this credit card number is okay, and here's your authorization. But you don't need to see the credit card number. We checked that for you. That was SET, and Visa and MasterCard actually mandated it, but everybody ignored the mandate. And the reason was extremely interesting. Big merchants use your credit card number as a database key. That's your identity at the big merchants.
Oh, man.
There was no way we were ever going to change that. No amount of mandates in the world. Because if Nordstrom says, okay, Visa, you insist that we don't use the credit card, see you later. We'll use American Express. Or we'll use MasterCard. They'll let us use the database, use the credit card number as your database key. So,
Interesting.
Yeah, it's very interesting. It was an infrastructure problem, a social problem, or a legacy problem is probably the best way to put it. Not a technical problem.
The thing is, though, I can understand why they chose to use your number as a key, in the sense that your number is guaranteed. My credit card number, if we could have the same name, but there's no way we could have the same credit card number.
Exactly right.
So for them, it's easier as an identifier.
That's right.
I can see why they did it.
Yep, it definitely
kind
makes
of scary.
sense. It is kind of scary, and that's why some of these disasters happen. Like somebody gets a laptop stolen and there are 100,000 credit card numbers on it. There've been a couple of cases like this. There was one with the Veterans Administration a few weeks ago. You remember that by any chance? And then there was
I don't.
There was an AT&T.
Oh
case,
yes, in Maryland, the guy lost his laptop.
Lost his laptop. Yeah. And I think that was actually Social Security numbers. But it's still kind of an unsolved legacy problem of having these identities in the having these essentially private key identities available in data as keys in databases. Technically, the problem is solved. You use a public key as your identity, not a private key. You keep your private key private on a smart card or on a thumb card or fingerprint. A lot of the new laptops coming out of these little fingerprint readers.
Sure.
Very nice. But the legacy problem is huge. There are all these databases that are filled with secret information, and it's a giant risk.
Yeah.
But another thing we learned about the banking industry is that it's all about managing risk. They know it's a risk. They assign a certain amount of number, a certain amount of dollar value to the risk, and then they trade. There are whole markets on trading this risk back and forth in the middle of the night, and then there are derivatives on it, just like derivatives on stock market risks. Oh yeah, there's people hedging their bets against these. I'll give you so many dollars as indemnity against stolen credit card numbers, okay? And then they bet.
Interesting.
And that's how this trading in derivatives work. It's massively interesting. There's people making fortunes on trading derivatives on credit card risk. The fact of the matter was that the way we got into this game was we knew that credit card fraud was $6 billion a year, and that was in '94. So we could save 10% of that. That's $600 million. That would easily pay for a little development effort at Microsoft, wouldn't it?
Sure.
Even as hungry as we are.
Yeah.
So that was the motivation for that. I had a really, really good time, and one of the outcomes of that was the current cryptography group in MSR. I wanted to stay in the product group after we shut down the SET effort. That cryptography group, Josh Benelo, Yakov Jacobi, Peter Montgomery, all those guys, we hired those, part of that. And they're now the crypto group in MSR. I sold them back into MSR and stayed in the product groups because I didn't want to go back to it.
So let's talk about that, though.
Okay.
I mean, in some sense, being an academic is nice if you're a pure researcher, for example,
Sure.
because you don't have to teach.
Yes.
So the other option would be, I work in Microsoft Research, but I don't have to build products.
Yes.
So what is it about building products that took you out of, because Microsoft Research is just pure science.
Yeah,
there's no mandate that says,
Nope.
I mean, it's nice if your research is tangentially related, and of course it is.
Yes.
But the point is, what led you to want to stay into a product team?
It's like drugs. Once you get a taste of shipping a product that 100 million people use, you can't go back. I can't. For me anyway. As a researcher, and I had a good research career, you write a great paper and there may be 400 people in the world who take notice. You ship Windows, if I wrote code that ships with Windows, there are hundreds of millions of people who are using that code. It's like the difference between, if you're an author, it's the difference between being James Joyce and being Louis L'Amour. James Joyce, wrote very erudite novels, and there are perpetual seminars on Finnegan's Wake to this day in English departments around the world, and there are 400 people who care. Okay. Louis L'Amour is the most successful author of all time, or at least he was last time I looked. He wrote over 400 novels and sold hundreds of millions of copies. They're westerns. They're good westerns, but that's the difference. Do you want to be James Joyce or do you want to be Louis L'Amour? No, I opted for Louis L'Amour.
Understood.
I really, really enjoy shipping product. The most important thing to me is to take ideas from the bleeding edge of research and put them in product and get them out there into the hands of people who can use them.
Excellent.
That's what I want to do. I have devoted my entire life to doing that.
Fantastic. And in fact, now that's a great segue into what you're doing today. We had Eric Meyer on Channel 9 just recently, and he works for you.
Yes.
And he's an incubation guy, and he's a scientist.
Yes.
And so you're running kind of a incubation-oriented team.
We are running an incubation-oriented team.
What exactly do you guys do?
What we do is take advanced ideas from programming languages and stick them into Visual Basic. That's my perspective on it. Eric has a slightly different perspective. But Visual Basic, we want to turn Visual Basic into not only the best and most popular programming language in the world, but the most advanced programming language in the world. By that I mean we want to take the best ideas out of the crazy research programming languages and put the mature ones into Visual Basic. Not mature by research standards. Mature by research standards means that all the researchers don't care about it anymore. They're done squeezing all the papers they can squeeze out of it. It's done. It's a done deal. They've dotted all the I's, crossed all the T's, and now it's old news. That's what researchers mean by mature. What we mean by mature is that we can tell that Joe Programmer can use this today to improve his life. And that's what we're doing. The main focus of Tesla is comprehensions. And what we're addressing is the infamous impedance mismatch in data programming. That impedance mismatch has many manifestations, but the worst of them is that the way to access collections of data is too strongly dependent on the details of that collection. For example, you want to access a relational database, you need to know that it's a collection of square tables with foreign keys and all of this kind of stuff. You want to access objects in memory. Well, you need to know that that could be a graph of objects with references to each other and possibly in a cyclic form. You want to access XML. You need to know XML is a node labeled tree. Objects in memory are an edge labeled graph. Relational tables are their own thing. The question is, and the question that we're answering is there some appropriate generalization of all these kinds of collections of things? And the answer is yes, it's a monad or a monoid. Monads and monoids are related to one another. Okay. Fancy word for collection of things. And there are a handful of operations that matter on collections of things. And guess what? They're in common for all of those. For relational databases, for objects in memory, for XML, you can access them all in exactly the same way. And the realization of that is the standard query operators in LINQ. LINQ, which I know you've done a bunch of these things on this.
Very interesting stuff.
My perspective on LINQ is that some time ago, the mathematicians figured out that the appropriate mathematical generalization of sets, trees, stacks, queues, decks, tries, priority queues, relations, all of those things, the appropriate generalization is a monoid. Monoid's a very simple structure. It's a collection of things with a way of putting two things together, and that's pretty much it.
Independent of what the things are.
Independently of what the things are. So the operations of putting them together, figuring out whether something is in the monoid, and it's a closed operation. Take one thing that's in the monoid, take another thing that's in the monoid, use the combination operator, you get a third thing that's in the monoid. So you never leave the monoid.
Don't leave the monoid.
Don't leave the monoid. Right?
There's a bumper sticker most people wouldn't quite get, but only you would. All right.
Actually, it's funny you say that because I was writing a tutorial on monoids for a while, and then I had to put it aside to actually work on the code. But I called it "Don't Fear the Monoids."
All right.
Now,
interesting.
The typical realization of monoids in programming languages is through a variant called a monad. And in a monad, the only difference is that you take things from a base set, which say is numbers,
mm-hmm.
and you lift it into the monad, and then you can't leave. So it's a little bit like, let's see, what's a good example? Here's a monoid, clock arithmetic, also called arithmetic modulo 12. The elements of the monoid are the numbers, let's call them 0 through 11, because it's easier that way.
Okay.
If you take any two numbers in there, take two numbers.
5 and 11.
5 and 11, add them up.
16.
Right, but your clock doesn't have 16 on it.
Uh-huh.
Subtract 12 from that, and you get 4. So if you take 5, add 11 to it,
mm-hmm.
you end up at 4, don't you?
Yes.
You go around the clock,
Absolutely.
Right? Yes. So all you do is just throw away every time you get 12, throw it away, throw it away, throw it away.
Okay.
You can add them up as much as you want. There's only one operation, that's addition.
Mm-hmm.
Once you get a number into the monoid, you can never get back out, though, because you don't know how many 12s you've thrown away. Right?
Okay.
So if you added, if you're back in just ordinary integers and you add 5 and 11, you get 16. And if you add 11 to that, you get 27. You keep going. There's no limit, right? If you're in the clock monoid, you keep throwing away 12s. You don't know. You can't tell the difference between 16 and 4, and between 27 and 3, and 38 and 2, and so on. Because you keep throwing away 12. So once you're in there, you're stuck.
Okay.
So that's the monadic way of viewing the clock monoid, the clock arithmetic monoid. You suck a number in there, and then it can never get back out, because as you add other numbers to it, you throw away all the 12s. Now, that one doesn't help for databases, but I'll give you another monoid.
Mm-hmm.
Monoid of sets. If you take two sets and you union them together, you get another set.
Mm-hmm.
That's a monoid. It follows exactly the same rules.
Okay.
If it's sets of integers, then you need to take an integer from the world of integers and put it in the world of sets of integers. We do that by constructing a singleton. You just take, say, the integer 5 and turn it into the set containing the integer 5. Now it's a member of the monoid of sets of integers. And you can union that with 1, 2, 3, and you get another set of integers that's 1, 2, 3, 5. That's great. Now, but you can't get back out.
Okay.
Once you go up, boom, you're stuck. This was all figured out 85, 87, something like that. Probably a little bit before that, when Monads hit I guess the main paper was 88 by Moggi, M-O-G-G-I, and then Phil Wadler got hold of it and made a career out of it, and there are some other people deeply involved in putting monads in programming languages.
So these are mathematicians, yes?
They're computer scientists with a mathematical, computer scientists with a strong theoretical mathematical emphasis.
Okay.
So one of the prettiest programming languages in the world is Haskell. And Eric is one of the creators of Haskell.
All right.
And Simon Peyton-Jones, who's at...
I just interviewed those guys last week.
Very good. So they're at MSR Cambridge.
Yep.
The way Eric and I got together is I was using Haskell over here to formalize a data model called EDM, which if you've interviewed Pablo Castro,
yes,
then you know about EDM. That's the entity data model.
Yes.
And in the early phases of development of entity data model, it needed formalization, which means that you just write it down mathematically. And I was using Haskell to do that, which was just a bizarre thing.
And that's a functional language, right?
It is a very pure functional language. It takes the ideas of functional languages and posits them without exception. It's like it would be a little bit as if you said, here's English grammar, and we're not going to have any exceptions to it. Throw out all the exceptional cases. So it doesn't let you cheat. Another very pretty programming language is called Scheme. But Scheme lets you cheat. It has ways of cheating. So it's not really a pure functional programming language. Haskell says, no cheating. You want to do something, you figure out a functional way to do it. And monads are necessary for modeling things like side effects and time-dependent behavior in a purely functional programming language. So by sticking to their guns, by sticking to the rules, the functional programming community figured out that monads were a beautiful way of encapsulating state. Now, real-world practical programming languages like Java and C# and C++ and VB, they always let you cheat. The cheating is called imperative programming. It means I just want to get my job done. Let me update variables and keep state and make copies of things and modify things in place. All of these things are anathema in the functional programming world because they don't fit standard mathematical models of functions. A function is something that gives you the same answer every time you call it. That's the definition of a function. A thing in a programming language, if there's state in there, you may call it one time, update the state, call it another time, and get a different answer. It's not okay mathematically. It's just simply, it's a non-starter. But that's the way real programming languages work. And of course, what functional compilers for functional programs, programming languages, take functional programs and turn them into imperative form, because of course that's the way real computers work. They're updating state all the time. So it's well known how to take functional forms and convert them into imperative forms. And then these so-called dirty programming languages, and I don't mean that pejoratively at all, but programming language like VB or Scheme, which is has some functional features but isn't purely functional, allow programmers to write stateful or non-functional programs directly. VB is, in many ways, is the best of all worlds in programming languages. We're putting in functional features. We're putting in lambda expressions and comprehensions, which are these comprehensions are the mathematical way of querying monads. It's let me hold this thing down.
Yes. Looks like a bunch of
it looks like a bunch of gobbledygook, but this is revealed truth here. These are the monadic operators for CLR languages. They're written in C#, but they work exactly the same in VB. This is filter. This is map. This is bind. And then there's order by and group by, which are order by will work if you have an I comparable on anything, and group by will work if you have a dot equals on anything. That's CLR lingo.
Okay.
But map, filter, fold, that's sort of like the functional programmer's mantra, map, filter, fold. And all you really need is fold. And in particular, all you really need is fold R, the right-handed fold. The left-handed fold can be written in terms of the right-handed fold.
Okay.
So in some sense, all you really need is this guy, select many, which is bind, monadic bind. And then you need a way of getting something into the monad. But this is what we've boiled it down to for C# and VB. The beautiful thing is this set of operators suffices for all queries that you want to do over objects in memory, over XML, over relational databases. It gets rid of the extrinsic, gratuitous differences amongst these various various shapes of data. Not completely, but enough that programmers don't have to deal with all the details all the time.
Understood.
You make some things easier for programmers, and you definitely make programs smaller. That's the big deal. Anytime you can show a demo at a talk where you say, oh look, I just took this 100 lines of software and I reduced it to 5 lines, you're guaranteed raucous applause. And 1,000 people will show up at your next talk. That's what everybody wants to do, is reduce the amount of code that people have to write and maintain. That's the big deal.
Absolutely.
That's where functional programming comes in. It's absolutely well-known, non-controversial, that functional programs are shorter than non-functional programs.
But harder to write for the novice.
They can be.
Mort level programmer.
Well, and now this is, you're pressing one of my hot buttons here with Mort, because I am the chief of all Morts.
Fair enough.
Remember, I'm a physicist. What I want to do is get my job done.
Mm-hmm.
I don't like programming. It's a pain in the neck. It's in my way. And if you can help me get my job done, I'm willing to spend some time learning a new way of thinking about things. If you can promise me that I don't have to write 100 lines of code, I can get by with 5 lines of code.
Oh, excellent.
With my performance provisos. Don't make it run 100 times slower. I might buy 2 times slower in exchange for 95 lines of code. This is the trade-off, right? Shorter programs are sometimes slower because there's more stuff going on. The compiler or the runtime is doing, there are higher levels of abstraction. Everybody knows that abstraction often costs performance.
But not always.
But definitely not always.
Mm-hmm.
So we're sensitive to all of these things. So I look at Mort, I look at my customer as myself. I put myself in the shoes of a physicist who needs to write a simulation and needs to get the job done. And I need just the right abstraction level. If it's too abstract, it may slow down on me. If it's not abstract enough, I'm awash in a sea of pointers and arrays. And I remember one program at Jet Propulsion Lab that it was written in Fortran, which was all we had, and it had 4 levels of arrays of indices to arrays because we didn't have pointers. You would look at one of these things and you would just, it would take you all day to get through 2 of these layers to try to figure out what was going on. And the reality was there were just a handful of people who spent their entire lives working on this program. I was working as a physicist on it. I tried to understand the program. It was hopeless. I could understand the mathematics that went into the program, and I worked on the modeling for it. One of the things I did was clock corrections for GPS, general relativistic clock corrections. 2 GPS satellites at 2 different altitudes will have clocks that run at different rates, just due to general relativity. The lower ones run slower, and these are very accurate atomic clocks on board GPS satellites, so they drift with respect to one another, and you absolutely have to correct for this. Okay. It's millimeter level of precision per year, and you add that up over time, you have to deal with it. So I was perfectly capable of doing all that mathematics, but putting it into that giant Fortran program was for specialists only, for the high priesthood. So that and other experiences convinced me that what I really wanted to do was make physicists into better programmers by giving them better programming languages, by helping them access high-level tools like relational databases. One thing I did for quite some time was science data systems. Scientists in general don't use relational databases if they don't have to, because it's a whole nother area with a whole nother programming model. And I already know how to use C or Fortran or Java or whatever. Don't make me learn this SQL stuff. I can put my data in files. My hard disks don't crash very often. I can back them up. What do I need this relational database stuff for? Well, you need it for all the other benefits of relational database: the atomicity, the go down the list, the isolation, durability, query optimization. Yeah, of course, there are many benefits, but it's too hard to use.
Okay.
So comprehensions, Tesla, we're integrate language integrated query. We tell people, we tell Mort, we tell the physicist, we tell me, it isn't that hard to learn. We'll integrate it with the programming language so that you don't have to learn something other than the programming language. You already know the programming language, we'll just give you some additional capabilities. The old way of looking at it was you would, the old ADO.NET, or you would literally write SQL, put it in strings, and then send it off to SQL database, where you're embedding one programming language inside strings inside another programming language. This is hardly a facile solution. This is just, it's yucky.
Understood. Well, but then there's still going to
That's a technical term.
You're going to still need to have stored procedures that do complex operations.
But then you have the high priesthood to do that for you.
Sure, right? You have the data dudes.
The data gurus will do the fancy stuff for you. But right, exactly right. Yeah. But Mort, I want to sit there and I want to get my job done, and don't make me learn stuff that I don't need. So
fair enough.
And that's really the motivation to make help Mort get his job done easier, and not by viewing Mort as a dummy. That's kind of wrong.
Kind of a bad name.
It's kind of a bad name. It's almost like Forrest Gump. You don't really want to. I don't know the history of these personas and so on. But Mort is a very clever guy. He just wants to get his job done. He doesn't care about programming language. He's not a programming language guy. He uses the programming language out of the box, and he gets angry at the parts of it that are hard to use and complains. And he loves the parts of it that are easy to use. So we want to take the more advanced stuff and make it easier to use. Tesla. That's in a nutshell. That's what Tesla is doing. Take it, advanced ideas, and make them easy to use in a standard programming language like Visual Basic.
And so, just so that we're clear here, with all of these names we throw around all the time, LINQ, BLINQ, on and on.
Yeah.
Tesla encapsulates LINQ and other related technology that you guys are working on. Correct?
Exactly right. Yes.
Okay.
Some of the related technologies are we need lambda expressions so that we can create functions on the fly that can be fed to these standard query operators like where and select and so on. To do lambda expressions properly, we need closures. They're not in there, so we have to do those. To make the query operators work properly, we need iterators. Those are not native to the programming language. We need to put those in the
for VB.
For VB, yes, C# has them. There are myriad other things.
Now let me ask you this. I don't mean to interrupt you, but
sure.
And I didn't get a chance to ask Eric this, although I think he did answer it without me asking it. But I'll ask it explicitly. Why are you choosing VB?
It's the shortest answer to the question is VB is the only language at Microsoft now. It might be the only language in the world that has both dynamic and static typing.
Okay.
So there are purely static languages like F# and C# and what was the other one? There's another one I'm thinking of. Java.
Yeah.
These are languages where the types of things must be known at compile time. Everything has to have a static type. Then there are purely dynamic languages like Python and Ruby and Perl, where the types of things are calculated at runtime. The distinction is a little bit subtle, but the point is what types do is reduce certain kinds of errors in your program. Instead of it being just a runtime error like a crash, it's an error from the type system that says, hey, look, you're trying to add an integer to a string. It doesn't make sense. Stop before you try. In a statically typed language, the compiler figures this out. Everything has to have a static type, so type of X is integer, type of Y is string. The compiler will tell you, you're never going to be able to execute this code. In a dynamic language...
Understood.
Yeah. You're never going to be able to run this code. What you're trying to do doesn't make sense.
Sure.
In a dynamic language, it actually checks this at runtime. So the compiler doesn't know that what you're trying to do doesn't make sense. The runtime says what you're trying to do doesn't make sense. So you actually run the program, and then it tells you what you're trying to do doesn't make sense.
But, one could argue that you're just delaying the inevitable, because either if the compiler says you can't add it into a string, which you can't do, then the runtime tells you can't add it into the string. It's going to throw an exception.
Yes, that's exactly right.
So, in essence, it's making it harder for the person who doesn't fully understand types, because VB people really don't understand types, because they've always been programming in a sort of that weird type of typeless language, sort of.
No.
They don't have the same notion. That VB.net then, of course, threw that on.
Yes, and that's all. By the way, I do need to preface this. I am only talking about VB.net.
Of course.
Yes.
Absolutely understood.
The old VB, wonderful as it was, it's not appropriate for any of the work that we're doing. VB.net is a complete change in the whole VB world.
Okay.
And it is precisely VB.net that makes VB attractive for Tesla, and more attractive than C#. Because we do have the dynamic typing capabilities in VB.net. You can opt in for late binding by declaring the static type of a variable to be object. Now the whole late binding machinery kicks in, and it works just like Python. What's the good of dynamic binding? As you said, it just seems to be delaying the inevitable, right? You're trying to do something that doesn't make sense. Well, here's the value of dynamic binding. You can make your entire program can be data driven. In a dynamic language, the actual code that you have to write becomes much smaller. Remember, we agreed that the big benefit is making the code smaller, and you push more of the specification of your program into data. So, for example, in an extreme scenario would be a test harness. If you have only static binding, then you have to write all your test cases, test 1, test 2, test 3, test 4, and they may be all different types, test 1 over strings, test 2 over integers, test 3 over floating point. In a dynamic scenario, you can write just one test loop, just say loop 1, 2, 3 over test, and whatever the type of the variable happens to be, just figure this out at runtime, please. It'll always make sense, assuming your program is correct, but it'll figure out that you're feeding it an integer, and it'll do integer things. And then the next time through the loop, it'll figure out that you're feeding it strings, and it'll do string type of things.
Okay.
So it makes the code that you have to write smaller. You write one branch, and you just feed it. You feed it variables of static type object, but dynamic type integer, string, and floating point. In the static language, you have to have 3 different lines of code.
Understood.
Fewer lines of code. That's the sole benefit. Do everything over there in the static world, you just have to write more code. Over here in the dynamic world, if you take advantage of dynamism, you can write fewer lines of code. So VB has both.
Okay.
You can opt in for dynamic binding by making the static type of your variables object, or you can opt out of dynamic binding and use static binding, and then your VB.net code looks just like your C# code.
Now, of course, C# could also be both dynamic and static if the design policy decision was made.
They may decide to go that way.
So, because then, the question I would ask is, it seems that many people are, for some reason, writing C# code when they want to play with .NET. They're not really programming with VB.NET.
There's a very good reason for that.
Let's talk about that.
The reason is cultural. Most people who come to C# come from a C++, a C, or a Java background. Those are all statically typed languages. They're just not familiar with dynamic typing at all.
Okay, cool.
They've just never run into it. They don't see the need for it. They're perfectly happy working with static types. The other side of the coin is people who come at it from JavaScript or Scheme or Python or OCaml or functional languages. Lisp. All of these languages are essentially in the Lisp family. They're very dynamic. And they don't want to have to declare all their types. They don't like it.
Sure.
They got to write more code. So those people want dynamic typing.
Excellent.
So VB is a confluence. It can give you one or the other, whichever you want. And I've blogged quite a bit on this. There's on my blog, I have some examples of.
What's your blog?
Okay, here we go.
Blogs.mscn.com?
Yeah. No, it's weblogs.asp.net/Brian Beck, BrianBEC.
Cool. We'll put the link up on with the video.
Yeah. Okay. Good. And I have all kinds of examples there. I got lots and lots of code, and showing all of the fun things that we can do with VB.net.
Okay. So we have a little bit more time left, but
Okay.
I think it's really interesting. I mean, we at the very beginning, you sort of brushed over the fact that you had this wave of physicists come to Microsoft.
Yeah.
So I have to ask. I mean, were you quantum physics?
I was a cosmologist.
A cosmologist.
Yes, astrophysicist,
Excellent.
relativity guy, anything to do with the large.
Excellent. And so it's ironic that you then decided to focus on operating systems and the small.
Yes. But that's because I don't know. I don't know. I couldn't resist the time warp operating system with messages and anti-messages and processes and anti-processes going backwards. How could any physicist resist working on something like that?
True. Now, do you think that anti-processes and anti-messages, that sort of world would make sense in a modern operating system?
Absolutely, totally would make sense. The time warp mechanism and the virtual time theory is absolutely applicable to any problem. All you have to do is identify what virtual time is. You have to map virtual time to something. In the case of discrete event simulation, we mapped it to simulation time. In the case of real-time programming, you map it to real time, and then the benefits of time warp are not so clear. The time warp mechanism gains speed up by executing things optimistically and then correcting mistakes when they're proved. So if two processes are communicating and one of them sends something into the virtual past of the other process, the
virtual past.
The virtual past is, let's say the process B here issued a command like, start dumping core, start printing thousands of pages on the, go into an infinite loop, launch the missiles. There's no limit to the damage that an erroneous process can do. But process A sends him a message into his into B's virtual past that says, wait a minute, don't launch the missiles. So B has to roll back and say, oh, I didn't really want to launch the missiles, and sort of undo that. So there's a whole commitment protocol worked out. So it doesn't actually launch the missiles until it can prove that no message could ever arrive in its virtual past. That's the commitment protocol.
Well, that's major redundancy against terrible mistakes.
Exactly. So we proved the system is correct. We proved it gets a speed up. It's every bit as valid today as it was then. Finding applications for it, the only challenge in finding applications for it is finding an interpretation for virtual time. That's it. When virtual time, if virtual time has to be tied to real time, then the speed up benefits now are questionable, because the optimistic computation doesn't really mean a whole lot when you're trying to do real time computations. But I was just talking with Eric the other day about how we could apply time warp ideas to his Ajax style scenarios, where that's where you want to write your program on one tier, as if you were writing it entirely for the client, and then sort of carve it into two pieces and deploy one on the server and the other on the actual client, without changing the code at all. Now you have inter-process communication and timestamp messages, and the whole time warp theory can apply if we can find an appropriate interpretation for virtual. What would that mean? Well, would it mean sequence number in a protocol? Yeah, it could be something like that. And, with simulation time, it's a no-brainer. The interpretation of virtual time as simulation time is a no-brainer. For other kinds of applications, it can be tricky to think what virtual time means. But the real analogy to pay attention to is that between virtual time and virtual address. Time warp works because time can be viewed just the way space is viewed. And so, again, you can see how a physicist could not resist this, right?
Sure.
Space and time are viewed exactly the same way in relativity theory. So why shouldn't we view them exactly the same way in computation? Well, the answer is you can. The working set theory for virtual address spaces was figured out a long time ago, And time warp, virtual time theory, is just an application of that to virtual time, where doing something in the past is like a time fault, just like accessing an address out of memory is a space fault. Works exactly the same. And we can get into all kinds of symmetries, like rotating around the diagonal axis, substituting space for time, maybe even Minkowski transformations and Lorentz transformations in Minkowski space. All of these kind of things, they do have natural analogies in the theory of time warp. Lots of fun to play with that stuff. Application to shipping software, I don't know. It's completely open book.
Sure.
Yeah. We may get there in Tesla. Right now with Tesla, we're focused on putting functional programming ideas, which is another area of beautiful mathematics,
Absolutely.
onto the street.
I mean, the other question I would ask is, why not make Haskell easier to write code in?
Oh, we are.
Okay.
It's called VisualBasic.net.
Outstanding. All right.
Don't tell anyone, though, okay?
Oh, well. It's already cast out of the bag.
Darn it.
Excellent. Well, I know because it's interesting, the software transactional memory people love Haskell because of its functional programming and great way that they hook into the compilation, etc.
It's a beautiful design language.
It's
probably the world's best software design language.
And Eric wrote that?
He is one of the creators of Haskell. It was a big committee. I have the book over there on my shelf. I don't remember everybody's name.
Sure.
But it was a big group that put that together, and Eric was definitely there.
Cool. So, you'd recommend other physicists to come work at Microsoft?
Absolutely. But you have to be a physicist who really likes programming.
Which is interesting.
I have some funny stories about this. When I was hiring programmers back in the early days, before everybody was a computer scientist, the 3 best programmers I ever hired were a physicist, a musician, and a dentist.
Wow.
Yes.
Interesting.
I had less success hiring mathematicians and computer scientists. Many of them just did not like to write code. They like to theorize about code. They like to think about code. But actually writing code and getting stuff to run didn't appeal to them as much. Whereas these people, the physicist, musician, and dentist that I hired, those were people who came to computing as a passion. They discovered it, and they said, "Oh, where's this been all my life? This is what I really want to do." I'm a little bit like that. Once I started using computers, I was always just a ordinary physicist. I didn't deal with computers, and one day I had to deal with them, and I realized that there was just fertile ground to be sowed and harvested there, because it was very primitive in the early days, very unpleasant, and for my thesis I spent 2 years writing software and 3 weeks doing physics. That's about the ratio, because it was so hard to do anything. And what I realized was that what I really wanted to spend my career doing was making it easier for physicists or Mort or anybody else who needs to write code.
Absolutely.
And functional programming is one way of doing that, and relational database, all these other things that we're involved in.
And that's clearly the future trajectory of everything we're working on as a company anyway. Right?
Absolutely. Make it easier.
.NET, et cetera, et cetera.
That's right. It's
Make
too
it
hard.
Composable.
Make it composable. Absolutely the best way to manage complexity is by building up complexity from small, non-complex pieces. Scheme is probably the purest and example of this. It states it even in the preamble of the scheme thing. Small number of ideas that are all composable with one another. The key word is orthogonality. If you can take one concept, like function application, and apply it to anything else in the language, that's an orthogonal concept. No special cases anywhere.
Excellent.
Yep.
All right. Well, on that note, thank you for your time. It's been
My
great
pleasure.
chatting with you.
All right. Fantastic.
And we'll come back and check out Tesla. We'll kind of.
Oh yeah, we're not going anywhere. We'll be at this for some time to come.
All right. So power to the Monoids.
Yeah, power to the Monoids.
All right.